Welcome to our Infoshare. It is called KMS Architectures and Services, and we are conducting this as part of our work in the GÉANT project, specifically in Work Package 6 for network development, and specifically in Task 1, where we deal with technologies and, of course, also with quantum technologies. We have 7 presentations today. We start out with our own expert who will give us a brief overview into the topic and introduction. And then we have 6 world-renowned equipment vendors that will present us their solutions to KMS architectures and services, and I'm very glad that all of you could join. The format will be as follows. We will basically have the presentations, and at the very end there will be a session for questions and answers. We will make one exception for John, who will have to leave early. You will be able to ask questions right immediately after the presentation. If you have short questions that can easily be answered in the chat, feel free to do so throughout the program. We will also record the whole session and make the link available on the events page later. Give us a couple of days and you will find it. So let's start with Piotr Rydlichowski from PSNC. He will talk about key management system for quantum key distribution network, concepts and integration with network services.
Thank you, Susanne, for the kind introduction. So as Susanne mentioned, I will try to be brief because we have a lot of very good colleagues today that will give us a very interesting overview of the KMS developments and the applications. So just as an introduction, I wanted to give just a few words about the KMS itself, what it is, why we need this, and what we can actually right now implement and use. So let me share the presentation. Why we need, just at the beginning, just a few words, why we need the key management system. So as I will not go to the basic of quantum key distribution. As we already discussed here, we have a lot of activities. So I think since we focus here on KMS, I will just move straight to the KMS issues. But as you probably remember, the QKD protocols and the infrastructure, the devices that we have, they are responsible for establishing the point-to-point links using different protocols, different physical implementations over the short or long distances. And we exchange over the physical quantum communication links, the random numbers that are interpreted as keys and can be used for various purposes, such as the encryption or authentication authorization, depending on our use case. And this part, for some of the protocols, we have information theoretically secure communication, but with the assumption to the protocol itself, not the implementation. We have to know that, of course, the implementation of the protocol is a different thing. And now the key management system is a crucial element if you want to scale and build larger networks that are comprised of those smaller links, point-to-point links, and it's a necessity when we want to establish a so-called quantum key distribution network. We need a dedicated layer, which is called QKDN layer, quantum key distribution network layer, that is responsible for establishing, managing, and taking care of this quality of service of the proposed and configured infrastructure. And also the KMS itself is an interface to the other layers, to the physical QKD network and the devices, and also to the applications that use the interfaces to pull and retrieve the keys that can be used in various services. And these reasons are why we call this quantum key distribution network layer, and can be viewed as a separate entity which is established within the network. Okay, and for the KMS system itself, regarding the functionalities, I gather here, in my view, I think the most important ones. So the key management system is responsible for retrieving the QKD keys from different QKD devices that we have in our network. Using the interfaces, they provide those keys. They can expose the interface that can provide the keys to the applications, to the services. It can store the keys, the KMS, based on the policies that we establish. The KMS can store the keys. It needs to be set up in a reliable operational environment. So this, because of this, it needs to have high availability, and of course backup links to allow the key management system to be always fully operational. We have also SDN implementation and approach for KMS, so we can use the principle of SDN to implement the nodes and the interfaces. I will give very short overview on that. And the KMS, since it's a separate entity, so we would like to have this as an interoperable system, so that can work with different vendors and different interfaces based on the standardization work. And also, we would like to have the KMS to be able to handle different topologies where the QKD devices, the physical links are established. And of course, we would like to have the KMS to be able to be integrated with PKI and hardware security modules infrastructure for a higher level applications and services that we have in our network. And because of that, we can look at the keys that we destroy and the KMS. We need to remember the life cycle of the keys within the system. So we generate the keys, we store the keys, we use the keys, and of course we need to destroy and dispose the keys based on the certain policies and assumptions that we have. So this is the elements that we need to remember, that we can use and we can also take care of in the KMS. And just a reminder, for in order to generate the key itself for the QKD link, in majority of the QKD devices, we have the several stages to generate the keys. First, we need to transfer the data over the quantum link. We use the sifting process, the error estimation process. Then we need to correct the errors based on the estimation of the link. Then we implement a so-called privacy amplification process, and at the end authenticate the process and the data that was exchanged. And after that, we can assume that we have the keys that can be then further processed within the system. And for the architecture of the QKD network, you can see the second layer. It's a key management layer. At the bottom, we have the key physical quantum communication layer, quantum key distribution network layer. So we have the QKD devices that which established, we have that exchange the data between the other nodes. So it's a pure QKD physical link between the different nodes. And as I mentioned, we established the link, we post-process the keys, and that are then processed within the key management layer. So based on the interfaces, we supply the keys to the key management layer, to the key manager. And as you see, between the nodes, we also needs to have the key management link. So it's not only the quantum key distribution link that we need to have between the nodes, but we also need to have the key management links between the nodes, between the key managers that actually exchange and process the keys. And within the key management layer, as you can see, we can store the key, we can relay the keys between the nodes, which is a very important element, especially if we implement the so-called trusted node to establish longer link. And we also manage the life cycle of the key, and we supply the keys to the upper layers, to the control layer, that actually then serves as an interface to the application and the service layer, where we simply consume the keys to our applications or services that we establish. And of course, so we need to think within the quantum key distribution network, not only in terms of the QKD itself, but also in terms of the key management links, how we process, how we secure them, how we expose the interfaces, and especially also the SLA that we want to provide for the links. So because they are tightly connected, and especially in terms of the services and the management. And in terms of the topologies, so we can have, as an example, this is the same as we have in the regular networks. We can have a different topologies of the networks. We can have a point-to-point links between the QKD nodes, and then the transient nodes, the intermediate nodes, they are called so-called trusted nodes. We can have the ring networks, also the star topologies, but we can also mix those topologies. And the key management layer is actually responsible for managing and tracking of the changes within the topology, and especially the backup links that we can have established within the KMS links. Also, in terms of I mentioned of the SDN, we also have a dedicated standard ETSI 014 that is focused, QKD 014, that is focused on the SDN approach. And then we established so-called, I will just briefly go here. So we established SD QKD nodes, which was responsible for the management and managing the layer and the transmission within the network. Overall, we have the SDN, of course, controller, as with our regular approach. And each SD QKD node is responsible for the key management functionality. Also, it has the interface to the different physical QKD devices, modules. And of course, similarly as with the regular SDN networks, we have the SDN agent that is controlling the operation of the node, and especially the nodes, QKD nodes that can be from different vendors that are used within the network. And also we have the application interface that is responsible for the handling of the keys. So this is SDK, SDQKD, and now if we want to think in a bigger scale, I just wanted to at the end, I wanted to give a few words about the EuroQCI overview. So as you can see, we have a different QKD networks that we want to connect. And also we need to have the possibility to interconnect those different networks that are managed by different KMS. And in order to do that, you need to have a topology of the interconnection between the KMSs. You need to be able to set up the paths to establish the link between the different QKD networks. The policies, you need to be able, if you can establish the link, if you can secure the link. So it's an ongoing process that can be done also on the terrestrial and the space link. So this is a concept that is being worked on within the EuroQCI. And just at the end, so in terms of the key delivery, I just wanted to remind you the ETSI 014 interface. So that actual interface, the most common in terms of they use the interface to extract and pull the keys. So we have we define so-called secure application entities that are the interface, and where we actually defined as a consumer where we can pull and extract the keys. We have the key management entities in each node that is used for key management purposes, and of course the quantum key distribution nodes that are actually physically providing the keys. And based on this, the architecture and the defined key and the defined syntax, we can extract here the status, so we can see the information regarding the key management entity IDs, secure application entity IDs, the number of the keys that are stored, how many keys, the size of the keys, how keys we can extract per request. Then if we ask for the keys, we can have the key and the key identifier. And then also we can query the interface itself regarding the status of the interface. Yeah, so this is just my short introduction. I didn't want to take too much time, and just to give the floor to our distinguished guests. Thank you.
Let us now continue with John Leiseboer from Quintessencelabs. He will talk about qConnect, a quantum-safe key distributor for QKD and PQC.
I was just going to thank Piotr for that introduction. I think you'll find there's a fair bit of overlap on some of my material, but I'll try to concentrate on the specific stuff for what we've done at Quintessencelabs. So I guess partially driven by customer demand and also as part of our general process of developing products for quantum safe networking, we've developed a product set, and I'm going to talk specifically about one of those products called qConnect, that attempts to, I guess, address the sorts of issues that we've seen in the real world. So, not to belabor these points, I'll just go over these very quickly. We all are in this industry as either researchers or developers or potential consumers of technology. We know quantum computing poses a threat. We know that, I should say the current situation is that we typically use cryptography to protect information that's being shared with various end users. That cryptography relies on public key cryptography for key exchange and digital signatures, and we currently have a high degree of interoperability, and the world would be a very difficult place to live in if we didn't have this reliance on public key cryptography. So that's the current situation. We're actually in a pretty good space if you forget about the next slide, which is the problem area, the quantum threats that come to these sorts of systems. So we have threats in that quantum computing can pose an issue with breaking existing public key cryptography. We have two technologies or two different ways of addressing this threat. One is through the post-quantum crypto algorithms. So a lot of work being done in various organizations around the world. In particular, NIST, I think, have put out a standard, and they're probably the go-to in most cases. Most other countries have a high degree of overlap or refer to the US NIST standards. But there are some issues with public key cryptography using the new post-quantum algorithms. We know that deployment will take time. We know there are legacy systems out there. We know that the standards that use public key cryptography, TLS, the AIT standard for IPsec, SSH, and other standards are still under development. They haven't yet caught up. And certainly post-quantum crypto hasn't yet been proven over any significant length of time. The other technology, which is probably more relevant here, is quantum key distribution. We need to, however, understand that there are some limitations with QKD only, point to point. There are key rate, distance, and latency issues for some potential deployments. And we also certainly have a lot of resistance in some parts of the world by some organizations to the actual allowing the use of QKD for key distribution. So these are the sorts of problems we've been presented with in trying to address quantum safe key distribution for our customers. What we came up with was this product called qConnect. We attempted to, in the product, introduce flexibility such that it can support both PQC and QKD either separately or together as the means for providing a quantum safe, in quotes, means of distributing key material. We've attempted to maximize interoperability. I mean, the ETSI 14 standard was shown on the screen a little while ago. That's one standard. That's probably the standard that QKD systems will support for delivery of keys, but we already have other vendors who have other interfaces into their systems that are not ETSI 14. An example there would be Cisco. They have the SCIP protocol. There's also Nokia that sort of use ETSI 14 for part of what they do with some proprietary extensions, and they use SNMP for something else of what they do. So what we've tried to do is look at how we can interoperate with QKD systems that support ETSI 14, but on the SAE side, the application side, how we can support other protocols as well. And then we want to overcome the technology limitations, specifically for QKD and extending reach, and some of the issues that we'd have with fault tolerance. Point-to-point network. If you lose that network, you've lost your communications. So we've developed this product called qConnect, and this is a feature summary that's on the screen at the moment. What we've done is we've provided the ability to support both PQC and QKD to secure links, either independently or together. So you can have both PQC and QKD running at the same time if you wished. We've entered the market with both a physical device, so a physical appliance, and we also have a virtual appliance, so a pure software instantiation of the system. For the physical device, you can obviously have we offer an internal quantum random number generator. That's probably more important for the PQC mode of operation, but it is also something that's of high value when we're looking at using the qConnect product as a trusted node. With the trusted node, you've got multiple QKD links. Obviously, the QKD key from one link is not going to be the same QKD key on another link, at least we hope it's not going to be, which means end to end, we somehow have to move keys around. We can choose to choose one link as the link that provides the keys to the application, or we might choose to generate an entirely independent key stream and then use the QKD keys to protect the distribution of that through the trusted nodes. So that's where an internal QRNG can come into play. For the virtual instances, network attached, and we can also get keys from QKD systems, obviously, so that's ETSI 14. I mentioned before the other vendors' protocols out there, SCIP and Nokia in particular. So we have developed a means for allowing the applications to use any of these three protocols on the slide, but the QKD system would communicate with that using just ETSI 14. So that's a way, it's still like a gateway function, if you like. Hybrid QKD PQC delivery, that's a little bit different to my first bullet point. We can actually build networks where some of the key distribution links use QKD, and some of the other links in the system can use PQC. So we can have a hybrid network in that sense. And in addition to what I said the first time, where we can have layered PQC over the top of QKD. So we have two layers of protection being provided there. Very important for performance and availability, some of the modes of operation that we have. So provider mode, basically we are generating the key material in qConnect. Pass-through mode, we're passing key material from a QKD layer typically up to the application entity. And these buffered modes that we have allow us to store key material for arbitrary periods of time, which means that we can lose QKD network connectivity, or we can be using slow QKD networks or intermittent QKD networks. And because we have this buffer of keys available, we can burst keys out and we can sustain delivery subject to buffer size and number of keys within those buffers, while QKD systems are unavailable. There's also the ability to have a network attached HSM as a root of trust to give us a validation story for the ability to use technologies that require, for example, a FIPS validation to prove security. quickly jump onto some of the use cases. I'll probably need to rush through some of these, and someone please keep time for me. I'm not actually monitoring time fully here. So simplest QKD network consists of just a link. We've already seen this diagram or a version of it. The way qConnect is deployed is it is deployed as an intermediate layer, providing key management for the QKD systems. So it sits between the KME and the SAE in a QKD network. Some of the benefits, I think I've talked about those with the previous slide, but basically we get PQC as a second security layer. We also have fallback to PQC for availability. We have the broad interoperability that I talked about. We have the QRNG. We have the key buffering. And as of starting at a very simple place, it also gives us the ability to extend to a more complex deployment. Speaking of which, this next slide here. So I've just sort of extended the concept of, the trusted node or trusted relay. Goes by various names depending who you're talking to. We all know what it does, but the idea here is to show that qConnect can actually operate as that trusted relay as well. Okay, and that allows for QKD's keys from one of the links to be delivered to the SAEs, regardless of how many links there are. It allows for QRNG generated keys from one of the qConnects to be the keys that are delivered to the SAEs and distributed in a secure fashion, through the trusted nodes. So both those options are available there. Benefits are all the ones you saw in the previous slides there. We now get the ability to support the redundant QKD links. So the mesh, arbitrary mesh networks, distributed from a hierarchical fashion, or loops, or anything in between the two. We get the ability to also mix QKD vendor equipment. So, different vendors can supply the QKD equipment as long as they support ETSI 14, everything works. And we're waiting for the ETSI 20 standard for trusted node interoperability to come out before we add that as a feature to the product. This diagram is something that I drew up to try and illustrate the hybrid approach, supporting both QKD and PQC, and also to show the ability to have arbitrary QKD networks. So that the orangey brown coloured plane down here shows, for example, 1 to 2 is just a standard QKD link between a pair of nodes. Then the location number 2 here actually has 3 QKD nodes in it, one talking to site 3, the other one talking to site 4, and you see site 3 and 4 actually have extra QKD nodes, so you can have a loop there, which gives us the ability to have multiple paths through the QKD links, which can then be taken advantage of by effectively like software-defined networking through programming the qConnect devices. They can determine the best path, and we can use things like adding costs to PQC links to QKD node, QKD links, so you can prefer to go one way or the other. We can also take advantage of dynamic capacity usage. So perhaps, node between 2 and 3 is becoming close to 100% capacity. If that's the case, we might find that we want to go from 2 to 4 to 3 for delivery of QKD key material. It might perform better than 2 to 3. So that sort of capability is provided in this upper layer. And also some of these links can be PQC only. So that green layer is effectively the qConnect product. The advantages there, we can operate PQC only, so without QKD, which is great for failure modes or for jurisdictions where it's frowned upon. Also, it supports what we call the last mile. So it might be advantageous for a telco to have a core network where QKD is being deployed for a really secure core network. But for example, there might be a campus or a building, an apartment building, or an office building where there might be hundreds of end users. It's probably not going to be cost effective to have hundreds of QKD links being deployed inside a campus or a building environment. So you might have QKD in the core, and then the delivery of the keys might be over local PQC protected links. So that's the sort of thing you can build up with that hybrid approach. Nothing to show on there. Nothing to show on there. And I think at that point, I'm probably close to my 15-minute time limit. But I just want to show one more slide, which is, I guess, similar to one we saw earlier. This is something we actually have deployed, and this is just demonstrating where qConnect fits in with different vendors' QKD systems. Typically, qConnect will be used to provide the end-to-end path for key material between systems. ETI14 from qConnect down to QKD, ETI14, SKIP, or the Nokia protocol to talk up to the transport layers. And then for more extended key management, we have other products as well, which is this very top layer. So I'll stop there.
So let's now continue with KEEQUANT. We have Jan Benda here. He will talk about a carrier-grade key management system, field deployment in DemoQuant, and the path towards a European trusted node QSplice.
Thanks again for having us, and I will talk a bit about how KEEQUANT tackles the topic of KMS. First, some introductory slide. One of the key features, as Piotr already mentioned, is key forwarding. So a quick overview of what that means. We have two end-to-end users that want to communicate, and they want to encrypt their communication, so they need some end-to-end key, and they need to each have the same key, so there needs to be some kind of key forwarding. The naive approach would be to just forward it directly over some classical communication channel, but that could be intercepted, and then your encryption efforts are more. And so we need to encrypt this or somehow protect this end-to-end key. And the way you would do that is using the QKD keys. So you would encrypt your end-to-end key using those QKD link keys from node to node. Each trusted node on the way, the relay nodes, would then use this QKD key to decrypt the end-to-end key. So that also means every trusted node would have access to the end-to-end key. And again, pass it on to the next KMS using the relative QKD link key again until it's at the final destination node. And now both of the nodes have their end-to-end encryption key that is only available to them and the trusted node along the way. So that was a quick overview of key forwarding and how that works. Now I'm going to go on to the DemoQuant project, where we explored the architecture of a carrier-grade network for the key forwarding. So that would enable keys as a service. That means basically that a user can request a key from this carrier-grade network, and the main difference is that the user is not in control of the central backbone of the network. And keys as a service and carrier grade, short overview, would just mean you request keys from the network as a user, and you are abstracted from the underlying mechanisms. And carrier grade would just mean all of the good qualities like highly reliable, redundant, scalable, and so on, low latency, fault tolerant, and everything we enjoy from existing backbone networks. A short overview of the architecture, how it was realized in the DemoQuant project. There were mainly 3 KMS types. I wrote out what these shorthands stand for on the left. And the way it works, the 2 secure application entities that want to communicate have their nodes on these outer limits. They have their user KMSs here and can now request keys from the carrier network. To abstract them from this carrier network, we have in the middle the access KMSs. They are used for authentication and authorization of this request. So are you actually permitted to get some keys and can talk to the other party? And then keys would be forwarded via the carrier network to the other party, and you would have that end-to-end key this way. And again, the abstraction is that you don't own the core backbone network that is used to forward the keys. That's why it's keys as a service, because you just request the keys. Okay. Then at a glance, the DemoQuant project, it was a QKD link from Bonn to Berlin over roughly 900 kilometers. There were 15 nodes along the way. We had 3 KMS vendors in this project that each deployed their KMSs on different nodes. We had 2 possible routes, which you can see here on the top right, that could be used. So we had dynamic route switching, and also explored how to react to security events, meaning if a trusted node was tried to be manipulated in some way, there would be a security alarm triggered, and all the KMSs around that node would purge their key store, meaning they assume the keys are now compromised and just generate new ones. And in this project, we developed, as far as our knowledge goes, the first intra-domain cross-vendor KMS interface. So that means we could seamlessly communicate across these 3 vendors and pass on keys to the key forwarding and everything vendor independently across these 3 vendors. And the architecture presented here is meant to serve as an architecture blueprint for future QCI deployments. Now one big problem, one massive big problem you could say with the DemoQuant project was that each trusted node had to be heavily armored. So there was big server cabinets that weighed half a ton each, and that comes with a high logistical effort. It's hard to transport, to install, to maintain. These big server cabinets are a big pain to deal with, and using something like that is not really scalable or flexible if you want to build large QKD networks. And now my colleague will present a solution that could work around this problem.
Yep, so thanks, Imo and Kanya from KEEQUANT. So just changing seats. So the solution, or rather the ansatz here, is that if you build up such a trusted node and you don't have this sort of armored cabinet, then what you typically do is you stack a bunch of devices, which is like QKD, key management, and maybe some sort of application and encryptor. But the problem is that the Ethernet patch cables between these devices you can tap, and the eavesdropper will always attack the weakest point. So if you just stack these devices and you have your Ethernet cables, then the eavesdropper will not attack the QKD link, but will just tap the key from these Ethernet cables. So the question is, so what do you do then? To provide a solution, you first have to think about what are the assumptions. And we divide into 2 types of sites here. One is like a trusted site, and one is we call it a trusted remote site. And whereas with the trusted side, you might have a guard that actually makes sure that nobody gets in. On the trusted remote side, somewhere in the woods, you may have a fence, you may have some concrete, but maybe there's no guard. So you're not as sure as you are for the trusted side. And one of the main differences also on the trusted side, you would also have personnel. So you will have plain text anyways. So you will need to make sure anyways that nobody accesses your plain text by entering the building. Whereas in some sort of remote site in the woods, maybe you don't care too much. For this sort of trusted node within the trusted site, it's probably not a big deal if you have those exposed Ethernet cables, but maybe in the woods you don't want them. And this is where the trouble comes in. That's why we make a distinction. And the distinction is to have either an end node, which sits in an actually trusted site, or a relay node, which can basically sit anywhere. You can put it in the woods and somewhere on the lawn, and you don't care anymore. Now what makes this difference work in practice? And this is where we introduce our concept QSplice, and I think this ties nicely back to DemoQuant, because for DemoQuant this would have been a 500 kilogram armored cabinet. But what we do here is we're developing a 19-inch for high Ethernet rack housing. So just a standard device that basically holds the QKD receiver, it holds the QKD transmitter, and it holds a key management system. And it's just fiber in, fiber out, basically. So you have one qSplice left, one qSplice to the right, one in the middle. And what the middle one does is act as a relay. It just splices these two things together and acts as a forwarding device. So it receives the quantum data from the left side, it transmits to the right side, and the key management system is the bridge in between. And now, why is this a novelty? I mean, this is how you would build up a trusted node, but what's really novel about this is that you add one tamper-resistant housing or tamper-proof housing around this. If you have this sort of 4-unit 19-inch rack device and it's actually tamper-proof, then you don't care anymore. Then you can put this in one device and it's just fiber in, fiber out, and it acts as a forwarder. And for extending the capabilities, one can, for example, add an optical switch to make the node degree from 2 to 3 to 4 and save total cost of ownership by having less QKD systems and just switching them, time multiplexing. And you can include the management of the device, you can share the RNG and so on and so forth. There's many options, and if you're interested, just contact us. We have a white paper on this. And with this, you can basically build your trusted node network. So you can have any sort of configuration. You can have end node to end nodes over a relay node. You can connect end nodes directly. You can have many different relay nodes in between. So there's all kinds of options. And what qSplice in the end is a Lego block that uses all of our expertise in QKD from DemoQuant and also from the other projects, and basically unites our products into one that you can just deploy and build your network with. And that's it from KEEQUANT side. Thank you.
Let us now go to AIT. We have Stephan Laschet, and he will talk about scientific thinking, industrial mindset, the AIT KMS for QKD networks.
Hi, thanks for having me. I am talking today with this title, Scientific Thinking, Industrial Mindset, a bit about the unique role that AIT plays in the whole ecosystem. So that also saves me time. I don't need an agenda. It's 2 parts. The first thing is more in theory. The second one shows our KMS a little bit more in action. So first of all, let's go to the scientific thinking. And also, thanks for my previous speakers. I can skip a lot of the stuff because you talked a bit about the ecosystem, the different standards, and so on. So maybe I rush through some of the points in order to take a bit more time on others that I think are a nice addition. So generally speaking, why is AIT special? Because AIT is a research institute. It's actually Austria's largest research institute. It's state-owned and publicly and privately funded, but that means I cannot sell you anything. So the KMS I show you today, you cannot buy it directly. The reason for it is, I mean, AIT sees itself as a bridge between the universities and the industry. So the KMS is a high TRL product, so it's rather on the right edge here, like if we take those bars as like the boundaries where we operate, right? But there is a clear boundary here for new products. I mean, we are state-owned, we cannot like be in direct competition to the industry. But we're working very close together with the industry, and maybe someday you can buy the product, maybe, who knows. But why is AIT actually developing a KMS? Well, we are a research company and we do research on a lot of different things regarding QKD. So we are researching on QKD hardware. Here you can see some outdated pictures of the lab, like but nevertheless, like on the physical layer, we have a post-processing stack, so a quantum post-processing system. It takes quantum events and makes a key out of it, basically through this pipeline that you already talked about. So it's only logical for AIT to also research on key management systems and also SDN topics for QKD networks. So this is the research landscape that we have. So we are part of a lot of different research topics, but all of them are very different. They might sound similar, they are very different. And for us, it was pretty good that we, from the get-go, chose a very modular approach in the KMS. So certain things that we only need for one project, we can enable and disable with certain modules. So here you can see I grouped them by different, like, let's say, use cases. So the first one is the military use case, which I think is also one of the prime use cases for QKD, because QKD is a very, let's be honest, expensive and very high security product. So military, state actors, that is the target audience that I think is the most prone to adopt QKD technology. So there we had discretion with a certain SDN focus. Also, some others here are in that consortium. Encore, which is an Austrian one, where we integrate KMS into an actual existing military communication system. Then we have industrial research. So first of all, Quarter, together with LuxQuanta, where we are also now in the process of deploying it in the Madrid network at Telefonica. And then eCauses with our colleagues of Creotech in Poland, where we deploy the KMS on the QKD system, so really as an integrated system. And there we put a lot of effort into certifiability. So the KMS will not be certified, as it's not feasible right now. But on the QKD layer, there's a lot of effort going into it. And this will be a very compact, very highly integrated system that I think has a great potential in the future. So also the other part that we are engaged in is the civil, governmental, and EuroQCI topic. So AIT is leading the Austrian QCI that is called QCI CAT for governmental use case, for example. And for critical infrastructure, that's another project that is very interesting. I mean, I can't talk too much about it, but yeah, it's very interesting. And in the other broader landscape, I want to mention Saga, which is a space QKD. We are actually developing the KMS for the Saga system. But I also cannot talk too much about it, and I didn't bring slides on it. So sorry, today I will only focus on our KMS that is designed for terrestrial use. All right, I think I can skip that one because we saw it already. Thanks, Piotr. And so also this is just another visualization of how it works. You know, you have to, for extending the range and to connect different parties, you have to connect all those point-to-point links and create end-to-end links from it. So, I mean, yeah, you know that each node has a QKD link. The KMS is a distributed system on each of the nodes. The KMS then collects all the QKD keys. And so that's maybe something we do is slightly different. So we have basically a big pool of QKD keys that we then dynamically allocate to the certain usages. So for external use, for different applications, for internal use, because we also use some keys for our authentication and integrity check, which I think is a very important point. So again, the QKD devices establish the direct links, and then, which you can see there, and then we just concatenate them basically and forward them. So I will go into the forwarding mechanism a bit later. Yes, but one important point is that since QKD promises information theoretically secure key establishment, we also must preserve that primitive on the KMS layer. So there are basically only a few selection of cryptographic algorithms that we can use for encryption. Everyone knows that's the one-time pad XOR. But very importantly, for authentication and integrity, you must use, or we use message authentication codes based on universal hashing functions. And I really urge everyone to really put an emphasis on this, because if you don't do that properly, an attacker could manipulate the key during forwarding. Yes, then it will not work. The two endpoints will have different keys, but you will not be able to detect this. So you really must make sure that the integrity and authenticity also is maintained, even though you could say it wouldn't matter too much because it's XOR encrypted anyways. But yeah, I hope I made my point here clear. All right, so it was already also shown, this picture, slightly different. This is directly from the ITU standard. I just wanted to highlight that the way we do key forwarding or key relay is same as it was shown by KEEQUANT. We are using an external random source. So here, that is the purple key. That is then also this key that is delivered to applications on that side. And we use the QKD keys basically as transport keys through trusted nodes in order to make the key available on the two end nodes. Okay, so I want to quickly just go through some additional things that the KMS layer has to care about. So key synchronization. I mean, you may or may not think that is useful, but whenever we get a key, we don't trust the key. And that is something that is like to the like paranoid behavior of zero trust, or like always making sure that the databases are in sync. And that actually saved our KMS execution a couple of times. Because you might think, of course, the QKD module gives the same key on A and B, but that is an assumption. You shouldn't trust that assumption. So we are verifying that the keys that we receive on both ends, so on node A and B, so let's, for example, this green key is actually the same key. So this way we synchronize all the databases, and as soon as we have synchronized all the databases, we can assign those keys dynamically, as I said, to a certain use. Of course, previously also mentioned key buffering. So when the QKD layer has issues, we still have a buffer, a reserve, basically to bridge gaps where the QKD layer might be down until we are maybe reconfigured to a different node. Key maintenance, so with that I mean like we have to take care of the keys properly handled. We have to reformat keys because applications need different key sizes, and therefore we need to reformat them to the appropriate demand. ITS encryption and authentication, as I said, but something also important that the first speaker was talking about is the PQC hybridization. And AIT is very much on the forefront of PQC, so we also submitted candidates to the NIST standardization efforts. So basically what we do is we establish the QKD key, as I told you, just a normal way. And then before we deliver a key, we hybridize it. So we establish a second channel with PQC and classical cryptography. So the standard stuff that is used today, plus Kyber Chem and Diffie-Hellman, dilithium signatures, sorry for the mix-up. And we derive a final key from those two. And from that, we get the best of both worlds. So let's say there's an implementation fault in QKD. We are safe because we still have the PQC channel. The PQC channel gets broken, well, we actually still have the classical one, but if that's also broken, we still have secure keys on both ends. Further, we get an end-to-end authentication because this node will authenticate directly with that node and not by proxy through the intermediate hops. Yeah, so KMS is also a pretty central part that was also emphasized before. And the scope is also pretty clear. The key management system, as the name says, manages keys. And you have the software-defined networking or network management layer that is handling the network management. So this is a really clear delimitation, I think, that is important to make. You don't have to do that this way, but we are following that approach, basically. So now I go into the implementation, and I can show you a bit about the KMS, how we develop it, and where we deploy it. So this is the team. That's me, Stephan Laschet. Sebastian Ramach is our main cryptographer and scientific contributor. We are working, like AIT, as I showed you, has a lot of expertise in QKD, post-processing, cryptography. So we have all the experts. So he's just one person that I wanted to highlight, but we are in a very, very good exchange with everyone on different technology levels. And then, of course, Luca Torresetti and Paul James as our main developers, main contributors. There are other contributors like interns or other developers that I don't mention here. I just wanted to show the core team. So this is where the industrial mindset comes in, because I and many of our developers have an industrial background. So we are doing basically test-driven development with the unit coverage tests, unit test coverage of like 89%. Currently, we're pushing it now to go beyond 90. We have static and dynamic code analysis for CI/CD, of course, with regular releases. We simulate this system, so we have a simulation environment in which we can just set up a QKD system. It's simulated, but we can then also make certain configurations that we really like to test, and we do that. Yeah, the KMS is a software solution, so it's deployable on commercial off-the-shelf hardware, but we also have some customizations for special hardware that we use. So the KMS is implemented in C++20. That also is very handy because the KMS is very resource light. It needs very few resources. That's very good if you want to integrate it, for example, as I talked in the beginning on with the eCauses project, maybe together with the Creotech QKD technology on one node. Then it's good if the KMS is not too heavy and doesn't require too much dependencies. The database, SQLite database, we use the cryptography library Botan for certain cryptographic things that was recommended by the BSI. When we deploy it on our hardware, on our servers that I'm showing you, we have a TPM that we use as a random number generator. We have also this SDN environment that is written mostly in Python and React, because that can be a little bit more heavy because it's usually deployed like alongside the KMS. And then HTTPS and CoRP for network communication. That's pretty obvious. Yeah, so this is basically what can the KMS do. And I can say all of those can be deactivated or activated. So due to this modular approach, you could, for the applications, use the ETSI-14 interface or also the ETSI-4 interface. And there you can choose between a co-op or an HTTPS connection. So on the transport layer, basically. And you can use both at the same time or either or, however you like. For the QKD layer, well, most of the time we are getting the keys with ETSI-14, but we have implemented in one research project a very, very interesting ETSI-4-based push mode, where the QKD device does not buffer keys, but it directly throws the key to us when it has it. So I think that's a really interesting use case. Like as I said, like all the cryptographic things that I will skip over because of time. And also we integrated with the network SDN interface. So I actually integrated with the QCool stack a couple of times. That will come later on. Yeah, and also, but also if you don't want SDN, you can also configure it statically. It's a lot of effort, but you could statically configure a whole network with our KMS. And we integrated with most of the QKD vendors. So I just wrote the European ones here, LuxQuant, I think Quantum, QTI, KEEQUANT, Quantum Optic Siena. So like physically, because in the Austrian network, we have all of those devices present. So we tested this with all of those devices. And this is just some pictures. So on the QCI days, which was a great event. So again, thinking fondly back of it, we showed the KMS. That's the one with the stickers here on like 3 nodes. In this case, it was KEEQUANT QKD devices and I think Quantum QKD devices. Different encryptors, Fortinet. We had like one WireGuard encryptor here. In the Austrian network, we have the ADVA encryptors that are integrated with the KMS. And for example, here's a Think Quantum device. We were also, like the military domain, I put an effort in the beginning. We were at the FANDEF, which is a military expo, to show QKD there, and also at a NATO event. But I'm running out of time, so that's why I leave you with a QR code that brings you directly to this URL, which is basically summarizing even more info, giving you more news and info about the AIT KMS. So with that, thank you. I'm looking forward to questions in the end.
Let us now continue with Jean-Robert Morax from IDQ. He will talk about drive Q-KMS adoption from research to large-scale commercial deployment.
Today, I will be more on the conceptual phase or conceptual presentation more than on technical. I will explain a bit ID Quantic situation, position in terms of moving from research to large-scale commercial deployment. Before going in detail, quick reminder about who is ID Quantic for the one who don't know. So ID Quantic is based in Switzerland. It's a company founded in 2001. Today, we are about 130 employees spread between Switzerland, where there's a headquarters, Korea, the US, Dubai, Singapore, and we have also an office in Vienna. In our product line, we have two divisions. One is for the quantum safe, that's a talk I will have today, and we have another one also for quantum detection system that is more specialized in time tagging and signal for the quantum detector. So before going into the discussing about the KMS, let's maybe refresh a bit the memory why we do QKD. So we know I will not talk too much about the quantum threat. I think all the audience know about it. I will focus more on the answer to this quantum threat, which is PQC and obviously QKD. Now, today, the quantum computer is not here, but still we need to move fast to adopt a security approach. And one of them is obviously the QKD. And why we need to move fast with QKD is because PQC is here. Nevertheless, we are at the beginning of the deployment, and there will be still probably issues that could arise, even if there's no quantum computer, just by the issue with implementation or some deployment limitation on the system. So QKD is, I will say, is a good alternative. Now, QKD also has some risk, and I will address later on about the topic about certification and security validation of the implementation. However, the big advantage of QKD is that if there is any issue with implementation, it doesn't scale, and it's really localized. Okay. But today we have already solution, and I will show later some of the products that do work in a live deployment. Obviously, at ID Quantic, we think that it's not one or the other, it's not PQC or QKD, and it seems that based on the previous presentation, it's a general agreement today that PQC and QKD come together because they both address different aspects and also are complementary enough in order to solve limitation on one to the other. QKD, to our standpoint, will remain mostly on the backbone and let's say the physical network aspect. So go from layer 1 to 3. It can serve above, but the use case will be a bit more rare. What is now very important for large deployments of QKD is integration with encryptor. So at ID Quantic, we do a lot of efforts to maintain interoperability with as many vendors, because if you don't maintain this interoperability, you cannot deploy the technology. So that's one aspect. Now, in the product, so obviously at ID Quantic, we have QKD. That's a core product. But over the years, we've also developed the quantum KMS. Okay, and our product is called Clarion KX. For the ones that have used our products, maybe you didn't realize that the Clarion KX was there because it's inside the QKD. Okay, so it's for many reasons we did that. First one is for security, so that it's inside the box, so you don't have no extra hardware. But also in terms of form factor, it's easier to deploy, and it usually serves most of the cases. Lately, we added a new product, which is a network appliance called Soteris, and this one serves different purpose. Okay, the first one is obviously when you deploy quantum KMS in a network, you may not want to be also locked in with one QKD vendor. So with this Soteris, you can also deploy other QKD system, not from ID Quantic, while still maintaining a one current approach on the QKMS layer. The QKMS layer here is really a key feature in the network because it ensures the currents of the security of the platform. This Soteris also is used in some instances where the KMS that run into the Clavis XG, Cerberus XG QKD system is not powerful enough to handle the consumer request. So it will be like typical for data center access. And also for some corner cases, and I think it was mentioned in the first presentation, you may, for economical reason, you cannot deploy QKD up to the last mile, then this Soteris will be able to extend the quantum KMS beyond the QKD network for specific use cases. Now, one of the challenge, and again, I will not cover all the aspect of what is required to, let's say, have commercial large deployment of QKD. I will only focus on a few items. One of them is obviously known to probably most of the people in the audience is certification. You cannot deploy a technology in the corporate environment, in a telco environment, is not certified. So today there's a lot of initiative going on to have the first layer, which is a QKD layer. So in Europe is Nostradamus. It takes some time. My guess is that it will still take 3 to 4 years before we can see the first product certified. But nevertheless, it's really something that is very important. It's moving forward at a good pace. At ID Quantic, we also work with national initiatives. And one of them was in Korea, where we got the first official certification of our QKD solution. And here it's a very interesting use case because they didn't focus only on QKD. So they cover QKD, the quantum KMS, as well as our crypto. Obviously, the crypto was not from us, so it's not depicted here on the screen, but they audited everything. It was, let's say, a very significant effort for ID Quantic. We worked for 2.5 years with a lot of resource on it, and we got the certification awarded in February this year. And now we start deploying this technology for high security network in Korea. But this is not, the end of the story. Obviously, in Europe, we also need to move forward, and we need to find a way to speed up the process to have certification. And obviously, maybe the quantum KMS is one aspect to have at least some kind of acceptance of the security of the infrastructure on top of the QKD while we wait for the full formal certification of the QKD layer. Okay. Now, how do you move from one phase to another? Here, it's more a story I will tell than explaining the step-by-step. So for ID Quantic, the first phase to build a network was, again, in Korea. And I will a bit emphasize this one because it was really interesting. It was in 2001 when we started the project. And the goal, it was a government-funded project, and the goal was to deploy a 800 kilometers network across the country. But they didn't want it, so they had several agencies that need to access the network, but they didn't want it to, let's say, multiply the QKD layer or let's say multiply the hardware per government agency. So they wanted to build one QKD network, but leverage this with different KMS networks. So we had to build a quantum KMS that could create virtually 3 layers of KMS. And this is also where we started developing the 020 protocol that is still unfortunately in draft today, but hopefully will be soon published and will be most probably adopted. We did that not alone, by the way. We did that in collaboration with Toshiba because here I just depict the ID Quantic part of the network, but there was another telco that also built another part of the network with Toshiba equipment. Nevertheless, so we had to build this 3-layer network to serve then all the different agencies that you see on the right. And obviously, the 020 was here just to interconnect the different layer of KMS so that the different agency, in some cases, could exchange keys in between them to secure data. So that was really the first phase in Asia. Then and here I'm refocusing on large network. This one was for a long time the biggest network outside China. Then in 2003, 2004, that we deployed with PSNC in Poland, also a large network. And this one is a bit more than 1,700 kilometers with a couple of nodes with all redundancy. It's still a star versus the other one that had the ring to provide redundancy. But nevertheless, this one is also providing some resilience to the KMS layer. So that was really, let's say, a big success in Europe. And with EuroQCI, there's other projects that will soon come live in this kind of dimension. Then last year, we launched together with Singtel in Singapore the first commercial network. And it's a very important milestone here because, sorry, it's changing automatically. So this one is very interesting because here the purpose of this network is really to onboard customer. So right now they are starting to onboard like financial institution and some public sector customer. And it's like, obviously the country is small. Nevertheless, it's an interesting network. So it's a ring with a couple of edge. And here they will build on the QKD layers, for the ones that know, they will do a one-to-one deployment. So that means in the center, you have one QKD Alice and that talk to multiple Bob. Obviously, this is really not on the KMS layer. Nevertheless, the KMS has a lot of to play to make that operationally relevant. So we are moving in the commercial aspect. Now, it's probably in the next year, there will be other large corporate networks that will also go live. Now we'll slightly shift. The focus is one of the challenge we will face as an industry when we start to deploy this kind of technology, that you will have to talk to CIO, Chief Security Officer, and so on, and they have some worries. Okay, so we come with a new solution that you deploy in the network, but even though it here to improve the security, it brings some risks. Okay, and here I took some examples. Obviously, they are not from our world. Okay, it's different service provider that are providing infrastructure to corporation, but we have seen over the past year that they were the main source of breach for their customer. Okay, so like big banks have very high security network, but sometimes they subcontract some of the service, and then the breach is coming from this supplier, and that's really a big problem. So now that we move slowly to, let's say, commercial deployments, all quantum KMS vendor, QKD vendor will need to move to the next phase of company maturity. And now we need to implement really a fully security approach, both at the company layer, okay, to have, so for instance, the standard ISO 27001 to manage all that your organization is very well structured, people, physical security, technology security on the IT side. Because obviously, when we deploy our system to the customer, even though we don't have access, we still keep some knowledge about the customer. We keep some information of the customer. And obviously, as our technology will be used for high secure network, we will be targeted to get access to this customer network. So we need to start also to build our skills, our capability in terms of security awareness. Today, I think all our I'd say QKD vendor and KMS vendor are focusing on this aspect here, probably some part here and here. So that's good. But then there is all the rest, all the security product life cycle. How do you ensure supply chain? Your provider, that they are secure. They don't embed like backdoor in the product that you use in your system. Manufacturing, assembly and validation, delivery and installation. How do you ensure that you deliver and install safely the system? How do you manage all the patches, security updates, monitor for weakness of all in the system? And obviously, you need to provide all the tracking information to the customer so they can identify issues in the network. Incident management. Incident management is not only for the customer; it's also for the vendor. If there's an incident, we need to support our customer to address them. And then the last part, which also sometimes we forgot, is end of life and decommissioning. Our solution will be used to encrypt very sensitive data. We need to make sure when they are decommissioned, they don't retain any secret, like maybe any keys or anything that could be used later to breach our customer infrastructure. So let's say it's a very let's say interesting journey. We are moving forward, at least on ID Quantic side. As a product manager, I see it. We are going in the right direction. At the industry-wide aspect, as I was also in the QCI days in Athens, I saw also a lot of awareness and moving forward on the technological aspect. Now we need to move also on the organizational aspect, and hopefully over time, all this industry will be very successful. So thank you very much for your time, and I give back the microphone for later question.
Let's now move to EvolutionQ. We have Christian Schmitz. He will be talking about building cryptographic resilience with BasejumpQDN.
Once again, thanks for having us here today. Before I start with the topic, I want to very briefly give you a short introduction in the company of EvolutionQ. EvolutionQ was founded by, three professors from the University of Waterloo in Ontario, Michaela Mosca, Norbert Lütgenhaus, and David Zhao. I think they are well known for their work in the community, still working as professors at the University of Waterloo, which means that our headquarters is located in Canada, in Waterloo. But we also have a headquarter here in Germany with an engineering team, which is led by myself. And we are working with customers to get them ready to be quantum safe, which just means we do professional services with them. We build quantum roadmaps to go into quantum migration, but we also have products, and we have our own qKMS. And whatever we do with our customers, the ultimate goal is to build cryptographic resiliency. And typically this is achieved through cryptographic agility, to be able to respond to developments or to emerging threats. But cryptographic agility doesn't protect you from catastrophic events, because cryptographic agility needs some time to react. Yeah, to be protected from catastrophic events, typically you need something like defense in depth, which is a combination of different cryptographic security mechanisms. And the third thing, which we think is very important, is the long-term security, mainly to protect you from threats like the harvest now, decrypt later. So we have different quantum safe technologies available today, and we have heard about some of them already. We have, of course, the post-quantum cryptography, and we have the quantum key distribution. We heard a lot about that, so I don't have to go into details. But there's actually a third category which we should have in mind, which is the good old symmetric key, which is considered to be quantum safe. And I'm not talking about things like key distribution centers like Kerberos, because you all know with symmetric keys, you have the n-square problem when it comes to the key distribution. But there are some companies that worked on solutions to leverage symmetric keys and the distribution of symmetric keys. And we think this is also one technique that should be taken in consideration when you build cryptographic, when you want to build quantum safe solutions. With PQC, we think the main advantage, PQC is fine, and the NIST algorithms are perfect and may be suitable for a majority of data out there, but the main issue is there's no long-term security when it comes to PQC. At least we don't have a proof for it. Quantum key distribution, I don't have to repeat that, costs, maturity, and so on, certification. So it also, we have different solutions, like 3 different categories we can build quantum safe solutions from, and we could also do combinations of these. So there is also the opportunity to use them in a hybrid approach. We have also seen some of these approaches before, which just means that you combine keying material from different sources And you can use the key derivation function with some classical public key cryptography using some post-quantum cryptography, appreciate key, or also QKD to derive a session key from that, which gives you the greatest number of potential security guarantees. So we can combine them, but we can also run them in parallel. But if we run them in parallel with QKD, and we already heard that, or we all know that QKD gives you ITS, information theoretic security. You want something which is maybe a bit stronger. And that's one of the reasons why we developed the multimodal protocol. The multimodal protocol is actually a protocol that combines different cryptographic primitives into one protocol that mitigates the weaknesses of each primitive on its own. So we use some classical symmetric keys. We have some pre-shared keys. We have a so-called key distribution hub, which is an infrastructure component that holds a shared secret between an endpoint and the KDH. And then we have like some classical public key cryptography like ECDH. We use some PQC, Kyber, and we use some pre-key data, which is derived from the shared secret between the KDH and the targeted endpoint. And we get some very strong security properties out of that. And these security guarantees are like, we have the long-term security, quantum resiliency, of course. We have perfect forward secrecy, post-compromise security, and also breaching the endpoints compared to the traditional KDC does not lead to any endpoint identity theft. Yeah, and we also it's a completely transparent protocol. A full description is publicly available. Also included is formal security about these security guarantees. And this protocol is actually part of our KMS system, which is called BasejumpQDN. BasejumpQDN is like the other Q-KMSs we have seen, a key management system for QKD devices, for quantum keys, which provides you with what a QKD, what a Q-KMS system does, like key buffering, key relaying, key forwarding, and so on. So it makes QKD networks, point-to-point networks, scalable and manageable. That's one thing, but with the same Q-KMS installation, you can also run the multimodal protocol. So if you have other endpoints which have not a fiber channel available, sorry, just via have a connection based on copper or Wi-Fi or whatever, or very small devices, you can use the multimodal protocol to provide them with keys with also very strong security protocols. The integration into the endpoint is always the same. So it's transparent for the endpoint. It's a seamless integration. It doesn't matter if you use QKD underneath or if you use the multimodal protocol. And you guess it already, we also have the option to run that in a hybrid mode where you have the multimodal protocol run in parallel with a QKD network, again, with a seamless integration for the endpoints, and you can choose on the KMS layer via the configuration whether you want to use a QKD key, a multimodal key, or a hybrid key. And looking at this infrastructure or this architecture from another perspective just shows you that this kind of hybridization also offers you with some scalability because of you have the limited distances with your QKD devices and the QKD systems. With the hybrid PQC, you can actually cover unlimited distances, and it also provides you with some backup. You have a fallback solution if one of the QKD links breaks, or the key drop rates for whatever reason. It gives you the opportunity to have the same, at least a similar level of security based on the hybrid PQC solution. It also offers you a transition strategy because you can deploy large-scale networks and you can replace links with QKD as it matures. And of course, we also have the satellite QKD coming. We are working with Spectral in Singapore in some projects. So BasejumpQDN will also support satellite QKD. And that gives you lots of options to build networks already today and transition to more and more QKD nodes in the future. When we talk about hybridization, you probably are aware that the security agencies and also the standardization bodies out there have different opinions about hybridization. Yeah, some of them, they allow or recommend hybridizations, others do not recommend them. It's also even not always clear what the position of one entity is looking at different sources or publications of these entities. Yeah. So therefore, with the solution that BasejumpQDN provides, you can configure, you can change it by configuration, and therefore you can actually meet all the requirements even if they are changing in the future. And the integration, as said, it's a seamless integration. So we have integrations into existing network OEMs like Nokia, Juniper, Cisco, Fortinet. We heard already about the interfaces here in other talks today. There are actually a couple of protocols at different layers that accept pre-shared keys. So actually that's what it is. It is a pre-shared key that is established out of band. So you can integrate them via existing standards into these protocols at different layers. And of course, we also have integrations in, I think, currently 14 QKD device manufacturers from all regions in the world. The deployment is also quite flexible. We have different components. There is the key agent, which is actually the QKMS part of the software, and there's the KDH, which is optional if you have if you go QKD only. There are different deployment options. It can be hardware-based on a hardened hardware. It can be software-based in a container or on a local server. And we also provide a custom SDK if you want to integrate it natively into your application. The KDH can run as a service, either operated by EvolutionQ or by another service provider. It can also run on a separate HSM, and you can also run this in almost any combination possible between these two, between these deployment options. So actually, that's with the design goals set, adding cryptographic resiliency, that's what we think we met with this sort of solution. The importance of cryptographic agility, the defense and depth approach, and also maintaining the long-term security, very important aspects. But also the operationalization is very important, integrating into existing infrastructures, the scalability, cost effectiveness, and also to be adaptable over the time. And yeah, basically that's from me for today. I'm happy to answer any questions later.
And now, last but not least, let's go to Qoolnet. Juan Pedro Brito will talk about orchestrating security, QKD SDN and KM in production networks.
let's start. First thing that I want to say is that here I am, let's say, I have a double hat because Qoolnet is a spin-off of the UPN, and that is now focused precisely on the integration of the quantum technologies into the current telecommunications network. So my presentation is about how we have evolved our initial, let's say, approach, focus on science to a product today. So in our research group at UPM, we were working on quantum cryptography from more than 15 years, especially in the context of quantum networks. And I would like to say that our first testbed was in 2009. It was highly coupled in the sense that we need to, let's say, tune the lasers and work with the CWDM devices to let's say, to maintain and establish a quantum channel, something very, very primitive if we see the evolution that we have today in quantum communication. But it was the first network established in Spain, here in Madrid, the first quantum network. But step by step, with several tests that we did, we see that this low-level approach was not the way to go, was not scalable, and we decided to switch to one disruptive approach in that moment that was, let's say, design this QKD network based on one disruptive paradigm 7 years ago that was software-defined networking. I think we were one of the first one to, let's say, to bet for this approach for the quantum network. In that sense, the first network that we did under this paradigm was on 2018, precisely in collaboration with the Telefónica team here in Madrid. And that was very, very important for us, very, very, let's say, a bit advanced, because with SDN, we can, let's say, have a lot of advantage. We can softwareize all the network. We can, let's say, trust on open interface, the coupling, the data plane, and also the control plane. We, let's say, can work also on open standards. And in other words, as I said, we can softwareize the network and accelerate the, let's say, the go-to-market of all this technology. So the SDN allows to move from typical model based on black boxes with a behavior that is not so clear, to more an open approach based on open models, interfaces, and protocols that give you the possibility to have, let's say, a grain control or great detail on how you can define the behavior of your network. You have, as you probably know, locally centralized control that basically this control works as the brain of the network. You have a full overview of what is happening into the network, so you can optimize all the key decision or the reserve of the resources for any application that is running into the network. You have a big abstraction into the network elements, so you can hide the complexity of the elements and only to expose the information that you need to orchestrate the resources. And also you have a, let's say, a simplification in the way that the back blocks approach require internal system, and in, let's say, in that way you can simplify what is required from for example, from the QKD vendors, because they can only focus on the quantum channel generation and relay the control on an external way. So the traditional approach, at least even for now, it's not very quantum friendly. The current infrastructure are not totally ready for this type of integration, but the high degree of freedom that we find with this SDN approach help us on the integration of the quantum technology in the current communication network. Following this SDN paradigm, we have deployed a few years ago what was the biggest and more heterogeneous quantum network ever built in Europe. Fortunately, today we have evolved, and some of the colleagues have even built biggest network, what is a good sign from my point of view. In that case, we had 4 different points of presence. We, let's say, managed 28 different QKD devices, all of them running simultaneously from different vendors, some of them based on discrete variables, another based on quantum variables. We have 9 hardware encryptors working in parallel from 2 different QKD vendors, one from ADVA, the other one from Rodan Swar. We also implement our software encryptor, layer 3 software encryptor based on IPsec. We manage 2 different domains. And also we have advanced features like QKD switchings and hundreds of applications running in parallel to stress the network and see that our solution was able to manage and orchestrate this network as a professional network. This is one of the nodes that we manage there, as you can see, with some Rodan Swar encryptor on top, the OEDM switches to have the add drop of the quantum channel, or SDN servers running our solution. Here you can see the ADVA OTN encryptors, and then 2 devices from IDQ that Robert presented a few moments ago, and another one from Civic that we collaborate in an annual project. So our proposal is, or what Qoolnet proposes, a solution to build and operate production-ready quantum-safe network. It's not only a KMS, but it's a full solution for that. This is again the image that we have seen today 3 or 4 times. I'm happy to see that in my colleagues because we were the parents that proposed this model, and here the main idea behind this scheme is that treat any QKD device as similar as possible as any other network element, trying to precisely is this integration. So in that case, the SDN control, the SDN, the localization control is capable of integration and optimizing the behavior of all of these nodes. For us in our approach and in general and basically on SDN approach is highly based on standard. We were one that proposed, for example, the 004 and the 015, and in collaboration with SK Telecom, we work on the 018. Are all of them European standard that helps on the integration in the QKD devices. For example, 004 and the 014 for the key delivery. They are, let's say, the objective is the same, but the way to do that is different. 004 follows a stream of key based on quality of service. 014 use more a transactional way to deliver the key. We give support for both of them. We also follow, for example, the network architecture proposal on the 017, and we have compatibility with the 018 in the current version that is right now. It's not approved, but we work on that. And of course, for us, there is 2, let's say, Rosetta Stone style standard, that the 015 and the 018, that are the SDN standards for, let's say, managing QKD, SDN QKD networks. This is a detail of what we have integrated all of this model here. This is the design of a software-defined QKD node. As you can see, we have the QKD system. We can have several of them in the same node. Then we have an SDN agent that is local control of the node, connecting every component that is inside the software-defined node. And inside of them, of course, there is one important element that is the key management system in charge of all the key material processed there. Then, for example, for communication from the SDN QKD node to the controller, we have the 015 interface, and from the controller to the orchestrator of the network, we have the 018 that is able to manage optical network in a separate way. Remember that you can have a decoupling because the QKD network and the optical transport network. As I said, the KMS for us is one of the modules in our approach, but we cannot forbid that the KMS, the regular KMS responsibility, are not the responsibility that we need in a QKD network. The KMS regularly is in charge of generation, exchange, storage, use, destruction, and replacement of the key. That is all the operations related with the key material inside the node. They typically follow strict norms on how to build this key management system, how we store the keys, how we derive the keys, like NIST 800-53, 56, or FIPS 140. The three, the KMS also use complex crypto giants that integrate a variety of algorithms and say many are able to serve to many users in parallel, and typically they are complex systems that are that pass high complex certified process for NATO, for governmental agencies, or military things. But in the case of QKD networks, we need also to solve some additional problems that are not common on this type of key management system, classical key management system, let's say. So we need to deal, for example, with some basically with symmetric crypto, that is the key material that we manage for the QKD node, and we adopt flow of symmetric keys among many devices simultaneously. So the KMS needs to deal with, in parallel, in general, with several links that are generating keys in a constant way. So also the key material that is generated is typically is ITS, information theoretically secure, and we need special functionalities like the management of different protocols, use different key materials, like, for example, not only QKD, but also raw keys. And currently, let's say the classical, the KMS, the QKD KMS is not so evolved as regular KMS, but the increasing the maturity to all of them to get these security levels. No need to deal. We need to deal with a variety of different QKD devices. There are several QKD vendors in the market right now, and typically deals with all of them, and needs to also work with what is common for us, but it's not common in the KMS system, that is the problem of the key transport. Key transport is not a problem that typically KMS need to solve, but we need to do it and need solve this problem. This is some of the features of the KMS that we using right now. As I said, for us it's quite important to use of the standard. In our case, our KMS is highly guided by quality of service, as for example, it is proposed in the 04. This is the standard interface that we expose in our KMS. It is ready, of course, for a continuous stream of key that is currently applications running on several of them. As I said, we tested our solution with hundreds of applications running in parallel. It's highly softwareized. We are able to extend even the functionality of the KMS according to the requirements of some of our possible clients, and it requires a minimal integration in the QKD. Say for us and for all of us here, I think we agree on the interface as a key element to do that. One additional advantage is you do not need to fully trust on your QKD vendor, because in the KMS you can also implement your security conditions or even your hybridized methods if you have a team that is able to do that. Or one important point here is that the key management for one plane that we implemented works in a transparent way with any QKD vendor. In our case, our SDN approach with this locally centralized approach help us to enable any end-to-end transport between any node of the network. Here, I can show you some of the proof of concept that we have applied in the recent year. For example, all of them in cooperation with several colleagues from the industry. For example, Tessie for video conference system, Roland Schwartz for the encryption layer, Los Quanta, QTI, Think Quantum, Quantum Optics, GÉANT Optics. So a lot of devices that we have the opportunity to integrate in this proof of concept and evolve to and show increase the state of the art of this integration process. Here, two of the most novel ones. This one was a few weeks ago in the EvolutionQCI demo, where we interconnect 4 different domains, and our solution were in charge of the key material of 2 of the domains. And the right one in collaboration here in Spain with Hospitales Vitas de Madrid, that was a commercial use cases using real connecting real hospitals with a full QKD network provided, in that case, for Telefonica, and an encryption layer done by Fortinet. So this is all from my side. I think I am more or less in time. Thank you. I am ready here to any question that you have.